smile and try to look good. So it is a great pleasure for me to introduce Chris Heunen from the University of Edinburgh, where he is working on quantum informatics. And I want to highlight, and he also has a new book out. But this is not what I think what you are talking about at the moment. But now it's your turn, Chris. Please tell us what you have to say.
All right, thank you very much, Jörg, and the rest of the organizers of the Atlantic Algebra Centre for giving me this great pleasure of telling you about tensor topology. This is something I've been working on for the past 5 years or something, and I'll tell you all about it. The main goal, so there'll be 4 lectures. I'm afraid they'll all have to be online, but so be it. And the goal of the 4 lectures is to build up to this picture in the bottom right here, where you can decompose any monoidal category into sort of smaller pieces that vary continuously in a sense. Now, Jörg was very optimistic when he put on the website that it's accessible to everybody, including undergraduates and your grandmother and everyone. I'm afraid it's not going to be all that open, but I have tried to make an effort to make it at least self-contained. So we'll start at the very beginning. If at any point you have questions, please just shout and I'll try to answer as best as I can. So what is this tensor topology about at a very, very high level? The way I see it, it's a sort of combination or interplay between, on the one hand, tensor categories, and the other hand, topology. And by tensor categories, I just mean monoidal categories. There's nothing like a linear enrichment or something, but tensor just starts with a T, and so does topology. So in that sense, it's nice. And also, there's already something that's called monoidal topology, and that's something different. So by tensor category, I really mean some way of combining processes together, both in series and in parallel. So if you look at this picture on the bottom left, these green boxes, you think of the green boxes as doing certain things to certain systems, sort of going from below to above. They take some input, they do something, they produce some output. And you can compose them in series, so next after each other, or in parallel next to each other. And topology, the way I see it, is a study of where things take place. So it's all about where things happen, where things live. And usually that happens on a topological space, of course. And typically people think of that as space because it's already in the word space. But you could think about a space-time, if you like, where the topological space of the manifold is not just spatial coordinates, but actual space-time regions. So we'll see how these two things interplay with each other. And we won't talk so much about applications, but this finds applications in, for example, concurrent computing and semantics for concurrent computing, where various processes in a single processor try and compute on the same input and do so at the same time, and sometimes send messages to each other, etc. This finds applications in quantum theory, which is where I come from, where you have several processes, again, that can work in parallel to some extent, but they can also be entangled and in that sense interface with each other. But nevertheless, one can be before the other, and there's some notion of where they act, where they live. And this finds applications in things like temporal logic, where now we think of the underlying space, not so much as a space, but like a timeline, where some formula can act here, another formula can act there, and they can sort of both be true at the same time, and what happens if they overlap, and that sort of thing. So that's a very, very high level overview. I chopped it up into 4 lectures. These are the topics I'd like to talk about in the 4 lectures. So today we'll talk about monoidal categories, the graphical calculus that they come with, that you can use to do computation with, and the Drinfeld center of a monoidal category. So as I said, I tried to start at the very beginning. Much of this is probably already known to many people, but it's good to all be on the same page, I think. Then next lecture, lecture 2, we'll talk about the very central notion of this mini course, namely central idempotence. This is a new thing, as far as I know, that any monoidal category can look at these central idempotents. There are certain types of objects, and they will play a crucial role. They will be something like the open sets of a topological space. We'll look at very many examples of monoidal categories and what the central idempotents in them are. And I'll build up some basic theory about these central idempotents and some little lemmas and propositions, saying that there's a notion of support, for example, that if you have a morphism, a process in this monoidal category, then, yes, go ahead. Or maybe I just misheard. Does somebody want to ask a question?
I think what you hear is the sound that is being made when somebody mutes and unmutes himself, but there's nothing. There was nothing actually being said.
Okay. Sorry about that. So I was saying in lecture 2, we'll talk about if you have a morphism or a process in one of these monoidal categories. There's a way to say where it supports, so where it lives, so which central idempotents are involved in it, where it acts. Then lecture 3 will go a bit more about topology, because so far it's only been the central idempotents. I say they behave like opens, but we're going to try and make that more precise. I'm going to talk about locales and frames and how you can do topology with just the opens if you have no points around, and how you might reconstruct the points. And mostly what we'll talk about in the third lecture is how this notion of pointless topology interacts with the monoidal category. And in the final lecture, the fourth one, we'll talk about sheaves. First of all, what they are, set value sheaves, and later on category valued sheaves. And we'll prove actually this decomposition theorem that I mentioned. At any monoidal category, you can see a sort of tiny monoidal category sort of continuously varying over this base space. And that's the prospectus. If you can't get enough, all of this is based on the papers I'm mentioning here. The first one is actually the book that Jörg mentioned. It's this one. It's very nice, and you can read it. And it's more for background. The real sort of tensor topology stuff is the 5 papers, the 5 lowermost papers. So I think we'll make these slides available afterwards. You can follow all the archive identifiers if you like. All right, so let's start with the stuff proper. Lecture 1 is about monoidal categories and centers. So just to be very, very basic, because undergraduates and your grandmother are supposed to be able to follow everything. Let's start with what a category is. So by category, I'm going to mean a set of objects, and I really mean set. All the categories I'm going to talk about. They'll typically call A, B, C, etc. And for any 2 objects, I want that to be a set of morphisms from A to B, and we'll typically call them FGH. And for every object, I want there to be a special map. So if you have one object, there's a set of morphisms from A to A. I want it to be one designated special map that we'll call the identity morphism. And that's sort of like the morphism that does nothing, if you like. Because what does that mean, doing nothing? I first have to tell you what it means to do composition. If I now have 3 objects, A and B and C, and I have a morphism from A to B and a morphism from B to C, I want there to be a composition, G after F, that goes straight from A to C. Right, so that's the little triangle in gray on the right there. And now I can say what it means to do nothing, because all of this data has to satisfy 2 requirements. The first one here is the identity law that says if I have a morphism F that goes from A to B, then doing F should be the same as first doing F and then doing the identity on B, or it should be the same as first doing the identity on A and then doing F itself. So first doing nothing, then F is the same as F, is the same as F and then doing nothing. And just to set notation here, you'll notice that by identity morphisms, I will sometimes write little ID subscript A for the object that they live on. But often I will just write the object itself as a name for the identity on the object. The second requirement is that composition has to be associative. So if I have 4 objects, A, B, C, D, and a map F from A to B, a map G from B to C, and a map H from C to D, then I can first compose these 2 and then tack on that one, or I can first compose the other 2 and then tack on that one, and that should be literally the same morphism. So it doesn't matter how I bracket the composition. Okay, so that's what a category is. What are some examples of these things? The very basic example that you will think about first, most probably, is where the objects are sets and the morphism between the objects are functions. Right? Because of course, between any 2 sets, I should say small sets, I guess, there is a set of functions between these two, and if I have a function from A to B and a function from B to C, I know what it means to compose these two functions. So it's a very, very simple, in a literal sense, category. A less simple, or slightly less simple, example of a category is where it's set to the power 2. So here object is going to be pairs of sets. So I have two pairs, one object consists of two sets. And if I have one object here, so two sets there, and one object there, two sets here, what is a morphism from here to there? Well, it consists of two functions. One
Sorry
from the first.
to interrupt here, but in set, I mean, you don't have a set of objects.
Yeah, sorry, set is a bad example. Let's say it's at most countable sets.
Mitya, did you say something? I didn't understand that, what you said.
I mean, in this big categories like set, there is no set of objects. Yeah.
That is right. So you say that Chris is using the word set a little bit freely there, but yeah.
I'm being a bit imprecise in there. So set is not really an example of a small category. I'm not claiming anything like that. I'm just trying to start at a very low intuitive level. Another similar example is you can think about vector spaces, maybe of some fixed dimension, fixed maximum dimension, where the objects are now vector spaces and it maps from one vector space to another is a linear function. Again, that's a simple example in a precise sense that we'll see later. A less simple example is if you take not just vector spaces over some fixed base field, but instead of a base field, you take a fixed base commutative ring. And now you take as objects a module over that ring, right or left doesn't really matter. And a map between two modules is going to be a linear function. A fifth example that we'll see very often is you take any partially ordered set, so that means a set with a less equal relation on it. I can view such a thing as a category by saying an object of the category is an element of the partially ordered set. All the elements of the partially ordered sets are objects, and there exists exactly one morphism from one object to another when this element is less equal than that element in the order. And because the order is transitive, I can compose these things, and because the order is reflexive, I have identity morphism, so this is a fine category. Now, I listed some more examples on this slide in black. I'm not expecting you now to know what they are, but we will introduce and use them later on. The first one is sheaves over a topological space, a sheaf of sets. And the second one is if you start with a locally compact Hausdorff space, you can look at Hilbert modules over the commutative C-star algebra that has a spectrum, that topological space. And you can build various free constructions of categories that satisfy certain things. So we'll meet these things later. I want to mention them now because they are examples that you could keep in mind while we go through all definitions and things, but I don't expect you to know them yet. Okay, I'm going to be talking about the graphical calculus. So if you just have a category, nothing else yet, there's a sort of graphical calculus that comes with this that uses one dimension. So I was talking about, objects A and B and a map F that goes from A to B. I could draw this if I wanted in a picture like that on the top left in blue, where F is the name of the morphism, has an input object A and an output object B. So you read the things going upward. So a morphism F will draw as a box like that. In particular, the identity morphism will draw a special box for that, namely the box that you don't see, and it's just the wire that goes from A to A. And then composition, I can draw as a composition of a map F that I draw as a box labeled F, and a box G that I draw as a box labeled G. I can just put the boxes on top of each other. And then the laws of categories, they say they sort of melt away. Because if I draw a composition of three things, you can't really see in the end picture the associative law. Right? If I first draw F and G and then draw H on top, that's literally the same picture as if I first draw G and H and then F underneath. You can't see what I drew first. And the same for the identity law. If I draw F and then sort of make the wire on the output a bit longer, you can't see the difference between that and F. Because I've been slightly cagey about this, but what does it mean literally to draw such a diagram? Because I put a box F in the middle. Let's say this picture on the right here. I have 3 boxes FGH, and my wires are a bit wiggly and the boxes are not neatly on top of each other, etc. But I'm going to think of this as literally as the same. I'm going to identify this picture with a picture where F and G are neatly on top of each other. So only the connectivity matters, not the length of the wires, not sort of where the boxes are. You can't really loop wires around, but they can sort of wiggle left and right a bit. All of that is fine. So if you just have categories, you have a graphical calculus to do computations, if you like, in this category that uses 1 dimension. Now we're gonna, for the next few slides, we're gonna add dimensions to this. The first thing I'm gonna add is I'm gonna not ask for a category, but a monoidal category. So by this I mean the following. If you have 2 objects A and B, I want it to be a third object that is sort of the object A's and B's put together. And I'll call it A tensor B. It doesn't have to be a tensor product, just any way of putting A and B together. And also I want it to be a special object I that we'll call the tensor unit. That's like sort of the empty system. If you think of A and B, A tensor B as the systems A and B put together, then you think of the tensor unit I as like the empty system. And just like we're putting objects together with a tensor product, I also want morphisms to be able to be put together. So if you have objects A and A prime and objects B and B prime, I can take their tensor products. But if I had maps from A to B and from B to A to B prime, I also want to be able to put those maps together. The last piece of data says something about what happens if I have 3 objects that I put together, right? Again, with some sort of associative way, I'll first put A and B together and then tensor C on, or I could put B and C together and then tensor A on. I want those things to be the same, but now I'm not going to ask that they're strictly equal, that they're literally the same object. I'm going to ask that there's a canonical isomorphism between them. So that means a morphism that has an inverse such that if I compose, I get the identity on both sides. And we'll call that the associator. That's typically called alpha. And similarly, if you have an object A and I tack on the empty system to the left, that should be the same as the object A itself. Or if I tack on the empty system I to the right, that should be the same as the system A itself. So I'll ask for natural isomorphisms of that type, and we'll call left and right uniters. Now, all of this data has to satisfy some requirements again. First of all these coherence isomorphisms, as they're called, alpha and lambda and rho, have to be natural. So, for example, the bottom left square about the left uniter says that if I have a map from A to B called F, what I could do is I could tack on an empty system tensor unit I on the left of A and to the left of B. I could do nothing on the I and F on the B, and then sort of forget the empty system on the B. Or I could first forget the empty system on the A and then just do F on the A. That's what that square says, should be the same thing. Same holds for naturality of the right uniter, naturality for the associator. And the triangle, the gray triangle on this page says that these things have to be bifactorial. So now if you have 3 pairs of objects, A prime, B prime, C prime, 2 pairs of maps, FF prime, G prime, I could do 2 things. First, I can put the pair of maps together to get F tensor F prime and G tensor G prime, and then compose them. Or I could first compose the 2 things of the pairs individually and then put them together. Both will be something from A prime to C prime. I want those 2 things to be the same. That's called bifactoriality. And finally, there's some coherence. These isomorphisms, associators and uniters, I want them to satisfy what's called coherence requirements. And that means for every 3 objects A, B, C, I want these 2 diagrams to commute. So the top one, the triangle equation, says that if I have 2 objects A and B, I could do 3 things to them. Either I put them together with a tensor product first to get A tensor B, or I could put on an empty system I to the left of B and then put it together with A, or I could put on an empty system I to the right of A and then put it together with B. Now they're related, these 3 ways of putting A and B together, by coherence morphisms. So the top one is an associator, and the downward ones are, I leave one of the 2 systems alone and I sort of forget the empty system in the middle. I want that diagram to commute. The other one on this page is the pentagon equation that says what happens if you have 4 objects. So So if you have 4 objects, you can tensor them together in various ways. I can bracket it various ways. If you start at the very left, I first put C and D together, then put B with it, and then put A with it. Going along the top, I could use the associator to swap the brackets around, first to AB together, CD together, and then to doing it all the way the other way around, where I put AB together, then C, then D. That should be the same as first leaving A alone, associating the other, B, C, D, then associating the whole thing, and then leaving D alone and associating A, B, and C. So these are 2 ways of getting from the very rightmost bracketing to the very leftmost bracketing, and I want these 2 ways to be the same. And this is, in a sense, enough, these requirements, because Maclane's coherence theorem says that, in a very rough form, says that whenever I have a diagram built using composition and tensor products from these coherence isomorphisms, associator, uniter, left uniter, right uniter, and identities, any such diagram will commute if it's well typed. And I'm not going to go into what well typed means. So as soon as these triangle and pentagon equations hold, all equations you could possibly imagine hold. Right, so that's what it means to be a monoidal category. And as promised, these things come with a graphical calculus too, and now this graphical calculus has 2 dimensions. So we already had that we can have these boxes and stack them on top of each other. That's the first dimension, sort of a dimension of time, if you like, doing one thing after the other. If you have this monoidal product around, this tensor product, you can also put things side by side, put them sort of in space together to do one thing while doing the other thing. So graphically, what happens is if I have a map F from A to B and a map G from C to D, I can put the objects together to A tensor C and B tensor D. I can put the morphisms together, get F tensor G. And we'll draw this as literally, F next to G, as in the top left picture here. So what that means is, if I look at, for example, the bifunctoriality law, a special case where 2 of the maps are identities, is this gray equation on the top right there. If you draw that in a picture, it means I have 4 objects A, B, C, D. I have 2 maps F and G. I start with A and C. I do nothing to the A. I do G to the C. And then after that, I do F to the A and nothing to the D. That's the same as sort of doing it the other way around, doing F first and nothing on the right, and G second and nothing on the left. Right? You can move these things around. That's why it's called the interchange law. And again, in the pictures, you can't really see the difference. These things sort of melt away in the graphical language. And a better way of seeing that is the lowermost pictures on this page. If I have 3 morphisms F, G, H, I can just put them next to each other, and you can't see in the picture whether I drew F and G first and then H, or whether I do G and H first and then F. And again, in these pictures, I don't mind if the lines are a bit wiggly, or if they're, F and G are up and down a bit, if the wires are a bit longer, or maybe I've shifted H a bit to the right over here. We'll make that more precise in the next slide, but I don't really mind. All these pictures we'll think of as the same picture. The picture on the right says something about the uniters. If I have a morphism F from A to B, and on the A object, I tack on an empty system I to the right, I'm going to draw this I very specially. I'm not going to draw it at all, or sometimes as a dotted or a dashed line, just to make sure it's there, but we don't really see it. Because if you think about things like this triangle equation, and compose that with an F, that really means that this I sort of melts away again. You can't really see it in the pictures, and that's fine because of the following theorem. So you can prove that this language is what's called sound and complete. In a sense, you can trade the algebra, in the sense of the gray equations here, for the pictures, the blue pictures. And you lose nothing in the translation. To be more precise, if I have a monoidal category, 2 morphisms in this category are provably equal according to the axioms. So that means the axioms being, triangle and pentagon and naturality and bifunctoriality. So if from these ingredients I can build a proof that 2 maps are literally equal, that holds if and only if the 2 diagrams I can draw for these 2 morphisms can be deformed into each other using what's called planar isotopy. By planar, I mean 2-dimensional in the plane. And by isotopy, I mean, if you look at these pictures, so pick one of these 1, 2, 3, 4, 5, 6 pictures, pick your favorite one, and imagine this as trapped between two pieces of glass. I put a box around it so they can't escape. So I have a square piece of glass. The input wires I nail fixed to the upper and the lower edge of this glass. So I have a sort of square glass here, and the things are in between there. And what you're allowed to do is within this glass move the boxes and the wires around, as long as they don't intersect. And you have to stay between the two pieces of glass. That's why it's planar. So if you have a frame planar isotopy from the one picture to the other, that holds if and only if the two morphisms that they represent are equal. And the two directions of this theorem are called completeness and soundness. Soundness means that the graphical manipulations are sound with respect to the algebraic axioms. So everything I can do graphically is valid algebraically. And completeness means the other way. Sort of everything I can do graphically, I can also do, everything I can do algebraically, I can also do graphically. So if you put the two together, that says everything you can do algebraically, you can also do graphically, and that's great. So we'll be using this relatively heavily. Now, since the pandemic, we've been told to not give 50-minute lectures or 100-minute lectures, but to chop them up into pieces. So I put some exercise for you in there. I'm not going to say anything for the next, let's say, 2 minutes or something. I'm going to ask you to do something. So get some pen and paper ready, or pencil. Because here are 3 things. You'll see 3 diagrams. I claim the leftmost 2 represent equal morphisms, because we can plainly see that there's a planar isotopy from the one to the first, where I sort of take this box H, slide it underneath the F, up between the 2 wires of G. And on the one on the right, I claim is not equal. In not every monodal category are these two morphisms equal, because there's no way for me to take the H sort of through the input wire to the G. So have a look at the left equation, see if you can write this out as algebraic equations, sort of in a big diagram like these kinds of things. And for bonus points, you can try and come up with a monodal category in which the rightmost 2 diagrams are not equal. And I'll just say nothing for a minute.
Before we do this, you should actually explain what this G means when it ends in nothing, or the F that starts in nothing. What does that mean?
Yes, that's a good point. So this box F here, all of the boxes so far had input wires and output wires. This box F, for example, has no input wires. So by that I mean it is a morphism from the tensor unit I to, in this case, let's say B tensor C. So it has 2 output wires, so that means the codomain of this morphism, the output, I can write as a tensor product of 2 things. And the same for G. So G has 2 inputs, but no output. So it goes from A tensor B to I, say. And specifically, H has no input and no output, so it goes from I to I. Okay, I hope everybody had a go. I don't actually expect you to finish this, because I did do this exercise, and the point of it is to feel the pain. So if you draw this whole thing out, let me put them side by side. So the leftmost 2 pictures over here are algebraically the path along the top and then the right, and the path along the left and the bottom of this big diagram. You see, this is quite an involved diagram. I'm not going to go through everything, but the magic sort of happens in, let's see, for example, this polygon here, where you do an alpha, then a rho, then a lambda. or you do a lambda, then a lambda inverse, then an alpha.
Actually, on my screen, at least, the diagram is too small to be readable.
I'll make it a bit bigger, sorry. Hopefully this is better.
Yeah, to some degree at least. Yeah, it's at least with some effort readable, let's put it this way.
But the point is that this part of the diagram commutes, because all of the morphisms are built up from coherence isomorphisms using nothing but composition and tensor products. And that's exactly what this coherence theorem says. These two maps are going to be equal just by virtue of how they're built. And I don't know, some other things, something like this square, for example, over here is naturality of the associator. And that way, all of the little filled in polygons in the middle, you can see commutes just from the axioms. And that means that the outer thing commutes. So the point is, this is quite painful to do algebraically. I mean, this took me a good, I don't know, half hour, say, to make this diagram. Whereas in these two pictures, it's dead easy. You can just see it visually, that you can take this H and shift it underneath the G. Okay, so for examples, we have the example of set and set squared. There you can think about the Cartesian product of sets. So if I have two sets A and B, I can take the Cartesian product, that's a third set. And if I have two maps F and G, I can make a new map that takes a pair of an element of A and an element of B, does F to the one, G to the other, and that gives me a pair of their outputs. So in that way, Cartesian product of sets makes the category set into a monoidal category. And the same for set squared. I can just take Cartesian product coordinate wise in pairs of sets. But you have other examples of monoidal categories. For example, the categories of vector spaces and modules over a ring. You can take the tensor product of modules. So this is something you've hopefully all seen before. If I have two modules A and B over R, I can build a third module A tensor B such that bilinear maps from A times B to some other module C are the same, are in one-to-one correspondence with linear maps from the tensor product to C. So that's a way to put objects together. And you can also put morphisms together by saying, what do they do to an arbitrary element of the object A tensor B? An arbitrary element will look like a finite linear combination of pure tensor things, little a tensor little b. Well, I just do F to all the elements little a, G to all the elements little b, sort of inside the linear combination. That's a perfectly well-defined thing, and that makes modules into a monoidal category. So that's the kind of things you can think about. I want to say a bit more about the Cartesian product of sets, because this is what category theorists call a product, which is the following thing. If I have two objects A and B, a product of them consists of a third object A times B with two projections from the product to the two factors. That has the following universal property. If there's any other object C that is like a pretend product that also has maps to A and B, then this pretender has to factor through the actual product in the sense that there's a unique map from the pretender to the product, such that the two maps factor through the two projections. That's the binary case. And in the nullary case, that means I have something like a terminal object that we'll call 1, such that for any object, there's a unique map into 1. So for example, this Cartesian product of sets that we used as a monodal product on the previous slide is an actual categorical product in this sense. Now, earlier we had the example of a partially ordered set regarded as a category. Such a thing has products exactly when it's a meet semi-lattice. So that means for any two elements A and B in the partially ordered set, there exists a third element, A meet B, such that another element C is below both A and B if and only if it's below the meet of A and B. And similarly, an object 1 is a terminal object in such a category exactly when it's at the very top, when everything is below that element 1. So in the purple picture on the right here, if you think of this as a Hasse diagram of the partially ordered set P, then 1 is at the very top, everything is below 1. And whenever I have 2 points A and B, you can look at all the things below both A and B. there's a third thing, A meet B, such that the overlap between the downsets of A and B is exactly the downset of A meet B. So such a semi-lattice you can think about as various things, but computer scientists like to think about them as, for example, in terms of security clearances. So I can have high access, I can have top-level secret access, I can have URIs only access, or I can have no access at all. And this is sort of, maybe I have access to the toilets but not the showers, and this forms a semi-lattice of the higher up you are in the semi-lattice, the more access you have, the more security clearance. Or you can think about sort of memory permissions. If you're a computer programmer, you're trying to write a certain piece of memories, maybe I can write to that part of memory, maybe I'm allowed to write to that part of memory. And if I have that, then I can certainly write to both of them. Or if you're a physicist, you can think about regions of space-time, where if you have some sort of space-time manifold, and the open sets of that form a meet semi-lattice, because the intersection of two open sets is again an open set. Right, so that's about semi-lattices.
Sorry, can I ask a question?
Of course, go ahead.
So in the example of regions in space-time, like, can you have a weird space-time where you have more than one meet?
So in general, for products, they're always unique up to isomorphism. So whenever two objects A and B have a product A times B, there's only one. If there's another one, it's isomorphic to that one. The same holds for a partially ordered set. If two objects A and B have a meet, then there is only one, right? Because in a pole set, isomorphisms have to be equalities. So in that sense, no, that cannot happen.
Okay, so you cannot in general define meets using causality of spacetimes, or you always have a unique
It depends a bit how you do it, of course. If I give you a manifold, you can make it into a partially ordered set in many ways. If you take like the canonical way of taking all the open subsets of your manifold as elements of your partially ordered set, then yes, they only have one meet.
Okay, thank you.
But you could make other choices. Let me skip this because we sort of talked about this already. And let me move to bradings. So far we had a two-dimensional graphical calculus. Now I'm going to talk about adding a third dimension to this. Namely, we're not going to have categories, which are one-dimensional. We're not going to have monoidal categories, which are two-dimensional. We're going to have braided monoidal categories. So a braiding in a monoidal category consists of a way to swap two objects A and B. If I have A and B, I can take their tensor product, A times A tensor B, or I can take their tensor product B tensor A the other way around. And a braiding is a morphism from this way of putting them together to that way of putting them together for any two objects A and B. And again, this has to satisfy some requirements. First of all, it has to be natural in the sense that if I do something to A and I do something to B and then I swap them around, it should be the same as first swapping them around and then doing something to A and something to B. And just like we had these triangle and pentagon equations before, there's similar coherence conditions here to make a similar coherence theorem true. This time it's called the hexagon, and there's two versions of it. Let's look at the left one. That says what happens if you have three objects, A, B, C, and you sort of swap things around. For example, first the A and the B, and then the A and the C. Or if I swap the A with the B and the C at the same time. So in a sense, this diagram says how the braiding interacts with the associator. And I ask that for any object ABC, any three objects ABC, this hexagon commutes and this dual on the right commutes. Now, this is not very pleasant to see at first sight. So you can also think about it graphically. So now we're going to have a graphical calculus. It's going to have 3 dimensions. I'm going to draw the braiding as a special kind of box that has as inputs A and B and as outputs BA. I'm going to draw it as sort of the A strand going on top of the B strand. So it matters here what's on top and what's on the bottom. We asked that the braiding is an isomorphism, it's invertible. So I'm going to draw the inverse as the thing going the other way around, where the strand on the left goes underneath the strand on the right. Then the fact that these two things are inverses graphically become the two pictures on the top right. That if you have two strands sort of laying on top of each other, you can straighten them out. Naturality is a picture on the bottom left, that if I swap two things and then do F and G on both of them, I could also first do F and G and then swap them. And this hexagon equation, this hexagon in gray on the bottom here, graphically becomes the thing on the bottom right. Whereas that says sort of if I have three objects A, B, C, I can think about B and C together as one object and swap that with A. Or I can think about them as two separate objects. So I can first swap A and B, and then further along the line swap A and C. And those two things should be the same. And there's a similar correctness theorem for this graphical calculus that says an equation of two morphisms are equal according to the axioms of braided monodal categories. Exactly when graphical diagrams that represent these morphisms can be deformed into each other by an isotopy. Now this time is not a planar isotopy, so it's not between two pieces of glass, but it's a spatial isotopy. You can use 3 dimensions to do it. So I don't put a frame around them and strap them between pieces of glass. I put a cube around them. I nail the inputs and outputs fixed, and I put them in, I guess, a glass box. You can move strands around within the glass box. So, for example, things you can prove then are pictures on the top, like here. I'm not going to make you do this, but algebraically, this is a similar headache as the big diagram I showed you before. So what you see here is you have some morphism, input I and output, let's call them A and B. And there's a third wire, let's call it C, that sort of either comes in from the left or comes in from the right. So at the end of the day, I have 3 things, A, C, B in the same order, but the way they built is sort of visually different. But because I can move this braid sort of over the top of the box, there's a spatial isotopy between these 2 diagrams. They're literally the same morphism at the end of the day. And same goes for this Yang-Baxter relation on the top right. This is a kind of famous equation that says what happens if you have 3 strands. I swap these 2, I swap these 2, I swap these 2. That's the same as doing it the other way around. First these 2, then these 2, then these 2. And indeed, you can see sort of visually that if you take pieces of string, then this is just true. You can deform one picture like that into the other. So the examples we had so far, most of them are braided monodal categories. For example, the category of sets. If I have a Cartesian product of sets A times B and a Cartesian product of sets B times A, of course I can make a function from one to the other by taking an element, A comma B, and just swapping the elements around. And the same you can do for category of modules, where if you take an element of A tensor B, which is a linear combination of pure tensors little a tensor little b, you just swap all of these little things around, and that's fine. On the bottom right here is a picture of are 2 pictures that are not spatially isotopic to each other. So there is a braided monodal category in which these 2 morphisms are not equal. Okay, and just for fun, I'm going to add the 4th dimension now. So we talked about categories, 1-dimensional, monodal categories, 2-dimensional, braided monodal categories, 3-dimensional. If you add a symmetry, that's going to be 4-dimensional. So symmetry is a braiding in which it doesn't matter if I first do the braid and then do the braid again. That's the same as straightening everything out. It's the same as equal to the identity. So that sort of means that the braid can sort of pass through itself. The over-crossing is the same as the under-crossing. So I might as well just forget about the over and under passes and just draw them as a cross. And again, there's a correctness theorem for this sort of graphical calculus, namely 2 morphisms are algebraically equal according to the axioms of symmetric monodal categories. Exactly when the pictures that represent them can be deformed into each other by an isotopy, this time it's a 4-dimensional isotopy. So if you like, you can imagine a glass box where now you get to color the wires inside, and they can pass through each other if they have a different color. So actually, most of the examples we saw already are not just braided monodal categories, but actually symmetric monodal categories. For example, set that we saw on the previous page. Swapping A and B is the same as swapping B. It's the same as the inverse of swapping B and A. But what's more interesting is for people that have heard about these things, if you start with a bialgebra over a field, for example, Hopf algebra, it could be a non-commutative one. I can consider that thing as a bialgebra, so I can look at modules over it. That's going to be a monoidal category. It's going to be braided, but it's not going to be symmetric in general. Another example of something that's not even braided.
No, it's not braided in general. Chris.
Sorry, yes, it's not braided in general, only if it's quasi-triangular.
Right, exactly.
Something that's not even braided in general is if you fix your favorite category C, you look at endofunctors on that category. But I haven't mentioned what functors are, so I don't want to say much more about that. All right, that's all about braided and symmetric categories. Now, for the last 10 minutes, let's say, I want to talk about if I start with a monodal category, how can I make it braided? There's a way of doing that. It's called taking the center of a category. So let's suppose, given a monodal category, I'm going to talk about what's called a half braiding in that category. So you fix an object U, and a half braiding is a way of sort of swapping that object U with arbitrary other objects. So you don't really have a braid between any two objects, but at least I can swap this object U with all other objects. So that means I want to have a natural transformation. For any object A, I want it to be a morphism from A times U to U times A for that fixed object U for any object A. That is natural in that if I do an F on the A before a swap or after a swap, doesn't matter. And that satisfies this diagram on the right that sort of says that the half braiding cooperates with the associator in the sense that, again, if I have two objects A and B, I can consider them together as one object A tensor B. I can swap that with the U, or I can do it in two stages. First swapping with the B and then swapping with the A. So this is the requirements I put on a half braiding. And it follows from these requirements, and this is a fun little proof that you can try if you want, that if every object, that the tensor unit, if you have a half braiding on an object U, let me go again. The tensor unit always has a half braiding on it that you can build as follows. If you have an arbitrary object U, you can swap that with the tensor unit by sort of forgetting that there's an empty thing on the left and then inserting the empty thing on the right again. So that's this equation at the bottom, which is sometimes taken to be a part of the definition of half braiding, but in fact it follows from these requirements already. So that's the definition of a half braiding. Any monodal category, I can look at a fixed object and ask, does it have a half braiding? Does it have more than one half braiding maybe? As we were saying, the tensor unit always carries a half braiding by forgetting the I on the left and then inserting it on the right or the other way around. And if I have two objects with a half braiding, let's say U has a half braiding called sigma, and V has a half braiding that we'll call tau, then the tensor product of the two objects also has a half braiding. It's built as follows. You start at the tensor product of U tensor V. You associate that to get the V apart and the A and the U together. You swap the A and the U. You associate back. Then you swap the V and the A. And then you make sure that U and the V are together again. That's what this gray diagram here, represented by the green picture on the bottom, says. So this is a picture representing the half braiding of U tensor V, given the half braidings on U and V. So what this means is, if you start with a monodal category C, I can define a new category as follows, that I'll describe, that we'll call Z of C, the center of C, the Drinfeld center of C, where objects in the new category are an object in the old category together with a half braiding in the old category. And a morphism from one such thing to another is a morphism in the old category between the two objects that cooperates with the half braiding in the sense that, first doing the half braiding and then F on the object is the same as first doing F on the object and then doing the half braiding. You can compose such things as in C. and it has identity morphisms. Namely, if I take an object U in the old category with a half braiding, I need to build an identity map on there, and it's just the identity map in the old category. It will satisfy this turquoise picture over there if you take F to be an identity, because that was part of the axioms of a half braiding. So in other words, and you can prove that this composition is associative and satisfies the unit laws. So if you start with a monoidal category C, an old one, I can make a new one, Z of C. That's at this point just a category that we'll call the center. But it's not just a category. It's in fact monoidal and braided monoidal at that. We sort of already saw the monoidal structure, because if I have two half braidings, I know how to put them together. And the tensor unit always has a half braiding on it. So we sort of know what to do, what the tensor product on Z of C should be defined as. But I claim it's in fact braided monoidal. So that out of thin air, this new category now has a braiding on it. This is a bit involved, and I'm not sure I can sort of reconstruct it looking at here, but I tried to draw it here, and this is what it is. If you have two objects in a new category, U with half braiding sigma, V with half braiding tau, I need to construct a braiding on them. So I need to make a morphism in the new category from the tensor product of these two things to the tensor product the other way around. Now the tensor product of these two things, by definition, is I take the tensor product of the objects U and V. So I need to find a map from U tensor V to V tensor U. And it needs to satisfy, because that was the definition of morphism, satisfy this turquoise picture. That first doing F on the object and then swapping is the same as the other way around. But now the swapping on the object is a fairly involved thing, because the object is U tensor V. So the swapping is this green picture on the bottom here that we constructed. So if you work all of that out, what you need to prove for this thing to be a well-defined morphism is this turquoise picture. And that just follows from the axioms of half braidings in the old category. So if you start with a monoidal category C, you can make a new category out of it, Z of C, the center of C, that is now braided monoidal. You've sort of created a braiding. There's a functor going back from the old category, from the new category to the old, that sort of takes an object in the new one, which is an object in the old one with a half braiding, and just forgets about the half braiding. And conversely, if C already had a braid, then there's also a functor from the old category to the new one. Namely, you take an object in the old one. What kind of half braiding are you going to choose on it? Well, I just take the braiding that already existed and fix the object U and sort of swap it with any other object. So that's the way to make a monoidal category braided. That's all I wanted to tell you about today. So just to summarize, really we're just setting the stage. I built up categories and the graphical language for them. We talked about monoidal categories, where you can not just compose morphisms in series, but also compose them in parallel, and the graphical calculus for them. That was sound and complete. It's a two-dimensional graphical calculus now. We talked about braiding and symmetries, where you now have 3- or 4-dimensional graphical calculus, where you can draw pictures like with these overcrossings and undercrossings and how they're different, and in the symmetry how they're the same. And the last thing we did is, if you start with a monoidal category, you can sort of make it braided by taking its Drinfeld center. All of that is just setting the stage, because next lecture what we're going to do is we're going to look at certain special objects in monoidal categories that we'll call central idempotents. And the central in here, of course, you can sort of tell already, has something to do with the Drinfeld center. And these central idempotents are going to turn out to behave a lot like open sets, if you like, of some sort of hidden base space. But that's for next time. And for now, I'll just say thank you. Bye-bye. Thank you for your attention. I'm happy to take any questions.
Yeah, thank you very much, Chris. Let's give him a hand. Well, Chris is definitely taking questions, but maybe forgives me if I make a comment for my students that are in the audience. From the Hopf algebra perspective, what Chris just described was is if the original category that he has is the representation category of Hopf algebra, then the Drinfeld center that he just described is the representation category of the Drinfeld double, as some of you have heard about the Drinfeld double already. So this is what I do on the Hopf algebra side with the Drinfeld double is what Chris just did on the categorical side with the Drinfeld center. This is the comment that I wanted to make for the people who have seen this in my lectures before, which brings me to the point that, by the way, next semester I teach a course on Hopf algebras again over here, which will also be Atlantic Canada wide and so will take place online. But other than that, so other questions?
Can I ask a sort of just a technical question? Well, not non-technical question. Will the recordings be available to watch? I know I can't attend all of these with my schedule, but it was very interesting.
We will definitely make the recordings available, and this will happen relatively soon. And they will be on the webpage of the mini course on the website of the Atlantic Algebra Centre relatively soon. Later today.
Okay. Wonderful. Thank you.
Further questions?
Is it appropriate to think of the Drinfeld center as being the objects which, or the morphisms which commute with everything in the category?
Sorry, I couldn't quite catch the question. Is it appropriate to think of the Drinfeld center as what?
As the objects and morphisms that commute with everything else in the category.
In some sense, that's right, but you have to read commute in the right way, namely sort of in the tensor product way, not the composition way. And as with all these coherence things for monodal categories and braided monodal categories, you have to really take care of these coherences. But in an intuitive sense, that's right.
Okay, thanks.
Chris, I hope you forgive me if I object to that. I would say it's intuitively right, but the Drinfeld center in a certain sense is larger than the category because it comes with additional data. So what it gives you the wrong impression is that it's only a subset of the original category. It is really it's an object plus data how to commute with this. And so it is in a certain sense larger than the original category and not smaller than the original category. So just thinking that it is a subset of this is a wrong impression. It gives you the wrong impression. Chris, would you agree with what I said?
Yes, I would agree with that. So the emphasis is very much on these, these half braidings and these coherences. So the object can have more than one half braiding, for example. So that sense is definitely not a subcategory.
So if I may jump in, so if you try to draw an analogy between Drinfeld center of a category and center of a ring, let's say. In the center of a ring, it's just a subset of objects that commute or elements that commute with everything. But here, we not only look at that they commute, we need to know how they commute. So there is this additional structure that performs this commutation. So that's the difference between the category picture and picture of a ring, let's say, and the center of a ring.
Yeah, that's a very nice way of putting it. Thanks.
Yeah, this is, Misha, thanks. Was also the point that I was trying to make. Further questions?
Can I ask a question, sorry?
Yeah, sure.
Okay, so you define the forgetful frontier from the center to the original category. So my question is, does it have a left join? And if yes, like, is it just when the category is braided, or you can have all the time?
It has a universal property that you can find in Street's paper, but I don't know it by heart, I'm afraid. It says something, no, it's not just a left adjoint, you need to have a section, I think. It's sort of chosen half braiding. So I don't know this by heart. I can point you to where you can find the universal property. I don't think there's a straight left adjoint like that, but maybe somebody else can jump in if they know by heart.
I think there should be, because in the Hopf algebra case, there definitely is. So
Right. Yeah, I was just going to mention that.
You can, if you have a module over the Hopf algebra, you can tensor it up to a module over the Drinfeld double, and I'm sure this is reflected in the categorical picture in some way, although it's not completely clear to me at this point how this really goes. Maybe Mitya knows this.
I think, I mean, it's more than just having a left adjoint that will classify the braiding, having a braiding to begin with.
If you can see this.
The additional condition is not just left adjoint. I mean, it's left adjoint plus ... which I've, again,
Yes.
as Chris said,
proposition 4b here, that's the exact universal property. So yeah, there is a universal property. It's a bit like a left adjoint, but you need to have this additional choice of this section here.
Okay, thank you. Thank you very much. So it's not like we cannot think of the center like a free kind of free elements of the category with braiding, right? We cannot think of it in this way.
I guess if you try and read it that way, what this says is you can choose these elements freely, but you have to choose them in a compatible way, which I guess comes back to what we were saying about it matters how they braid around, and they have to be in a coherent way.
Yeah. Okay, thank you. Thank you very much.
Can you say what this paper was that you just showed us, Chris?
Yes, it is this one.
Oh yeah, okay. Mm-hmm.
This is kind of handy actually in online lectures. You can just dip into the library.
That is true. That is true. Further questions? We are still recording, by the way, so don't be embarrassed.
I have a couple questions, actually.
Go ahead.
First, when you were talking about the soundness completeness theorem of the graphical calculus, does this mean an alternative method for proof when you take things up to planar isotopy is to define literal homotopies between your pictures and do things from a ridiculous perspective in that way?
You can take this up a notch and talk about two categories and monoidal bicategories or weak two categories. And there are similar theorems for that. I say theorems, but I don't think anybody has worked them out in the literature. But the consensus is that there is such a theorem, yes.
Okay, thank you. And
the two cells become homotopies.
Well, and I was asking also for your the exercise you gave us.
This one?
Yeah, when you take your, say, bounded box, there's no homotopy moving the H under or over that string. And would that constitute like a valid proof if you went things about that way?
You mean for this inequality on the right?
Yeah, yes.
To falsify that equality, you need an actual example of a monoidal category in which the two things are not equal.
Okay. Okay.
So if you can build such a thing out of homotopies, sure.
Awesome. That helps me see what I missed also. So that's good. Thank you.
I think, Chris, if I'm not mistaken, a bimodule category could be used to give a counterexample of what you of the problem, that inequality that does not hold in this picture, right? Where A
that could well be. I haven't tried that before, but it could well be true.
You mean like you would take a non-commutative ring?
Right, a non-commutative ring, and tensor product is over this ring.
No, that in itself can't happen because there's this bit I skipped. Where did that go? This. If you look in a monoidal category, you look at maps from the tensor unit to itself. They always have to be a commutative moment.
Right.
In particular, if you take Nevertheless, if it equals over a bi-algebra and the bi-algebra is over a field, that is a fine monoidal category because the field is monoidal, because the field is commutative. So that's what I had in mind when you said that could falsify this right equality. So if you take a quantum group and look at its representations, I can well imagine that will falsify the right equality.
What do you think about that? I'm not so sure.
I'd be really interested in seeing this written down. I'm somehow skeptical.
I've seen this discussed in the book by Tourayev and Virilizier, the green one. I have forgotten what the title is. They have a special name for things which have the property that you can move the H over that. But I've forgotten the details at the moment. Further questions? Geoff, you had more questions?
It disappeared.
Okay. Other people, further questions? Well, if that is not the case, then we come slowly to an end here. We started a little bit late, but I think that's everything worked out perfectly. As I said, we will post the recordings later. And we say bye-bye to everybody at this point if there is nobody else who wants to say anything. Chris, do you want to say a final word? No.
Last words.
Yeah, okay, famous last words.
In 2 days.
Okay. All right, then see you guys on Thursday, yeah? All right. Bye-bye.